few facts. We have increased the amount of CO2 in our atmosphere as a result of our fossil fuel use. We've been measuring this in the atmosphere directly since the 50s, and we are now up to 393 parts per million by volume, which is 40% higher than before we started building fossil fuels. So this is a fact that humans have affected the amount of greenhouse gases in the atmosphere. So how much has the climate warmed because of that? Well, this is the observed change in surface temperature over the last 100 years or so, a little bit more. And overall, the average change of the planet is only 0.85 degrees C, right? And notice that that would be, and I'm going to use my pointer. It's kind of hard to talk and into this microphone and use the pointer. Is that still okay? Yeah. Okay. 0.85 is about here, this red. So much of the planet is around that, you see. But you can see some places are much, much higher than that. And those places are, on average, are up at the higher latitudes, right? Where the planet is by nature cooler, and so you add a little heat and you get a lot more bang for your buck, right? So the average warming, people think 0.85 degrees C, that doesn't sound like so much, but we have the potential, especially in our neck of the woods, to have a lot greater change than that. The last 100 years is at least 4 degrees Fahrenheit warmer, putting it in Fahrenheit, which we're more familiar with in our neck of the woods, which is up here where we're in the purple. Another thing to be concerned about is the fact that snow cover, right, in our hemisphere has decreased over the last 100 years. Another and very important thing to be concerned about is the amount of sea ice in the Arctic Ocean, right? This is permanent sea ice, and it comes and goes, but in the summer it gets to its smallest extent, right? And we're actually getting down to where we might not have any in the summer. And in fact, they projected that to happen in just a few years, in 2015, that we might get to none. When you open up the Arctic to ocean instead of sea ice, it changes the energy balance of the planet in a huge way, because ice reflects a lot of the incoming heat and water absorbs it. So we're going to change the energy balance of the Earth and kind of go over a tipping point at the time that this ice disappears. Another thing that has happened and been documented by scientists is the amount of heat in the ocean has changed. And it has risen relative to what it was. And this is, you notice this data doesn't go back as far because we haven't been measuring the heat content of the ocean all the way back to 1900. But just in the last 50 or 60 years, it's changed quite a bit, about 1%. And this is where you would connect the increase in severity of hurricanes and cyclones. So the more heat there is in the ocean, that's where the storms get their energy. The more heat there is in the oceans, the more you're going to expect bigger storms, stronger storms, and more often. Global sea level change. Now, you don't hear too much about sea level change that's already occurred, because so far it's only been 0.2 meters, so about 190 millimeters. But projected to the year 2100, it's much higher. We'll come back to that. This is one of the things that most people are not aware of, and it's something probably for one of our greatest areas of concerns, which is that when you have more CO2 in the atmosphere, more CO2 is actually absorbed into the ocean. And when you change the amount of CO2 dissolved in the ocean, you actually change the pH of the entire ocean. And the pH of the ocean is critical for many organisms that make calcium carbonate shells. And there are a few that have a boundary at which they just won't be able to calcify anymore that we're getting close to. Not all of them, but some of them. And the further along this goes, the more the whole ocean biological system is going to be threatened. Now, you're probably familiar with the fact, we already talked a little bit about the fact that the temperature records for different parts of the world vary. These are diagrams showing the actual data from different continents and different parts of the world for the warming. Notice that the warming is the black and black lines, right? The red swatches, they're not really lines, are the results of models, as are the kind of blue-gray lines here. Now this is actually the smoking gun for is the amount of the CO2 that we're putting into the atmosphere, the smoking gun for climate change. This is what's causing it. And this is, scientists have shown that when you do models with only natural forcing, so only what's going on with the sun, things that are going on with volcanoes, and only those things that we know very well, the amount of, and let's look at the global averages on the bottom here, the amount of warming that you would expect on the land surface, this is 1910 to 2010, you may not be able to see that number, is, you notice that it's pretty flat. But when, in red here, those models use both natural and the anthropogenic greenhouse warming, then you actually match those observations, right? And this is why scientists are 98% sure that it's us. And notice that the same is true for land surface, when you add land and ocean surface, because the oceans have warmed, and even just oceans, right? That there is a difference, and it's clear that we are doing. Okay. So now let's move into what the IPCC group, and this is hundreds of scientists from across the world, are predicting for the future. Notice that these are their predictions, their RCP. The important thing is the number at the end. This is for assuming a smaller amount of radiative forcing, and this is for assuming the greatest amount of radiative forcing. And that's radiative forcing as in heating caused by CO2 addition to our atmosphere. And so this is change in surface temperature from our time period to 100 years from now or so, okay? And you see that if you assume the smallest amount of warming, we still have pretty significant change, and that change up in our neck of the woods is, and this is in degrees C now, right, is close to 2 or 3 degrees C, maybe even 4, right? Actually, we're down here, so it'll be 2 or 3 degrees C. If you assume the worst, right, and one of the things to mention is that we've been doing this for over a decade, these predictions. And in all cases where they talk about what are the ranges of how much CO2 is going to be in the atmosphere for the future, we're always on the highest end. Humanity has not cut back at all. So unfortunately, we're on this track right now. To have our temperatures basically planet-wide very, very different and much warmer than they are today, 100 years from now. Now notice that these changes in average precipitation are much more mixed, right? Temperature for sure is going to go up everywhere. With precipitation, and this is why there's some winners and losers with global climate change, there's going to be places where they get wetter and some places get drier. And on average, the places that are already wet get wetter and the places that are already dry get drier. Precipitation is not quite as well constrained as temperature. Now this really brings it home to my students when I talk about this, because we all know what it feels like to have heat over 100 degrees Fahrenheit. It's hot, it's unpleasant. Here's how many days, now these are, you probably can't see these numbers, this is number of days over 100 degrees Fahrenheit, and it goes from less than 10 to over 120 is the darkest red. And you notice that in the 60s and 70s, we had mostly 20 to 30 days, somewhere in that range, across the country, and here is probably less than that, above 100. Now, what they're projecting for lowest emissions is that in Texas, basically a third of the year is going to be over 100 degrees Fahrenheit. If we have the highest, if we just don't stop what we're doing, go business as usual, that's going to be us too. And that, to me, really brings it home. To have 62 months of over 100 degrees C in here in Twin Cities is an incredible amount of warmth. This is a prediction about precipitation in our neck of the woods. And this is summer and winter. Tom Johnson and John Pastor are going to talk to you a little bit more about what's going to happen in our region, or what has happened and what is likely to happen in our region. And notice that in terms of precipitation, this is millimeters per day, the pale colors are fairly close to The blues are positive, the yellows and oranges are negative. You notice that we are kind of right in that region, and this is again with the lowest warming up to the highest warming. The numbers on the top have changed a little bit, don't worry about that. It's a little bit hard for them to predict, but not huge changes in precipitation. Potentially in the summer a little drier, and in the winter a little wetter. Sea level is projected to rise. I mentioned this before. Business as usual, we're going to get up to potentially a meter of sea level rise. What does that mean for us? Well, here we're a little insulated from that, being in the center of the continent. But if you have a home in Florida, I don't recommend buying coastal property. A lot of the tip of Florida would be underwater with a meter's worth of sea level rise, and New Orleans would be in a world of trouble. Now I'm going to pass it over to Tom.
Good afternoon. I'm going to tell you a little bit about what we know about Lake Superior and what kinds of changes we observe going on in Lake Superior. I'm also going to say a few words about other Great Lakes around the world. And in fact, I'm going to start out with that. With this remarkable statistic, which is half of the fresh water on the surface of this planet is found in only 4 lakes. That's our Lake Superior, Lake Baikal in Russia, Siberia, and then in East Africa, Lake Tanganyika and Lake Malawi. Those are the 4 largest lakes on Earth. They hold half our fresh water. It's amazing. Now there's a lot of water in the ground. This isn't counting groundwater, but this is the low-hanging fruit of water. In all 4 of these lakes, it's clear blue water, it's high-quality water, it's very easy to extract from the lake and use. Lake Superior and Lake Baikal, the commercial fish catch every year is something like 3,000 tons of fish. In Lake Malawi at the south end of the East African Rift Valley, it's not 3,000 tons, it's 70,000 tons of fish. Lake Tanganyika, it's 200,000 tons of fish. This is cheap animal protein for the people that live in the developing world. So these lakes are incredibly important to us. I'm a faculty member in the Large Lakes Observatory at UNLV. We're like a small oceanography department. We're part of the University of Minnesota Duluth. We have 10 faculty, about 20 mostly graduate students with some undergraduates working with us, and staff, technicians. We operate the Blue Heron, which is the largest university-run research vessel on any of the Great Lakes. We're not just looking at the fish or the biology of the lakes, we're looking at the chemistry of the lakes, the physics of these lake systems, how the water moves, how it responds to the winds and temperature and so on, and geological features on the lake floor as well. Now, as you drive up the North Shore, you might have noticed buoys such as this out in the lake. It's probably one of ours. Attached to these buoys are a cable that extends down to the lake floor, and on that cable we have a number of temperature recording devices that allow us to measure temperature every minute over the course of a year. And so we're looking at the internal dynamics of how the lake works from these kinds of measurements. Here's a temperature record for Lake Superior that extends from 1910 roughly on up to about 2005 or so here. The trend is continuing in that upward direction. These are temperatures measured in the St. Mary's River, the water intake plant at Sault Ste. Marie. But we can make a direct correlation between those temperatures and the temperature of the surface water out in the middle of Lake Superior. So the trend in the middle of Lake Superior is the same as this. And basically what it's showing us is that Lake Superior, and we were really surprised when we found this out, Lake Superior has warmed by about 2.5 degrees centigrade over the past century. This is twice the amount that the air has would have thought this huge, big, cold, massive lake would be very reluctant to change its temperature at all, and yet we're seeing a measurable change in the lake system. So what does this mean for the lake? What's going to happen? And that's not an easy question to answer. We're learning more and more about the lake using a variety of state-of-the-art technology. And this is one of the instruments we use. It's called a glider. It's an autonomous underwater vehicle. You can set this in the lake. It's a torpedo-like device. It's about 8 feet long. We can set it in the lake at 2 harbors and send it on its own way. And it'll dive and come up, dive and come up, dive and come up, and go across to Fort Wayne, where it is programmed to turn around and go back to 2 harbors, and then programmed to turn around and go back again. So we can remotely have this device measuring a number of properties in the water: the temperature, the chlorophyll in the water, which is a measure of the algae, the pH of the water, the oxygen content of the water, the turbidity of the water. And I want to just give you a sense of what we're seeing with these kinds of measurements. Here's a profile extending from 2 harbors on the right across the lake to Fort Wayne, Wisconsin. And this is a profile of chlorophyll concentration. Basically, that's telling us the abundance of algae in the water. And the algae you can think of as being the grass in the pasture. This is the base of the food chain. This is what ultimately feeds the zooplankton, which feeds the small fish, which feeds the large fish. So this is the grass in the pasture, all right? And we see that there's not much at all in the deeper part of the lake. That's 50 meters or 150 feet depth there. Not much at all there. But up in the top, we see these hot spots of a lot of algae, then lower concentrations, and then hot spots again. Now, the next few pictures I'm going to show are day-by-day changes in that structure between the 3rd and I think the 9th of September in 2011 when we ran this particular experiment. And here it goes. And you can see that it's moving, the concentrations change. From day to day they change. And it's like this lake is breathing. These internal waves are making these algae concentrations go up and down. They're shifting. Sometimes they're hotter over near Minnesota. Sometimes they're hotter over near Wisconsin. And it's a very complex system, and we're just beginning to have the technology to fully understand just how complex it is. Imagine 20 years ago when our biologists would go out on the lake to make measurements of biological productivity. And they would just take one spot measurement off 2 harbors, sail over to Fort Wayne, make another spot measurement, sail out to Isle Royale, make another measurement. Very useful measurements, but they're completely missing the dynamics of this system. And the point of showing this is to underline the fact that as the lake warms, we're going to see the dynamics of this pulse of the grass in the pasture change in ways that we still don't know. All right, so we're working on physical models of circulation of the lake, of chemical models of how the biological activities take place, how it responds to higher CO2 in the atmosphere, how it responds to warmer temperatures. And the bottom line right now, the bottom line answer is we don't know what's going to happen with warming in Lake Superior yet. We can also learn something about the history, the historical trends. Are we seeing any changes in the lake that are more than natural variability? And so we can get at that by taking sediment cores from the lake. This is a coring device that we use that takes short cores of sediment off the floor of the lake and enable us to look at, say, the last 100 to 200 years of accumulation of, say, contaminants like PCBs or mercury in the bottom sediments. Whereas this is a longer coring device that we deploy that can give us a longer record of change in the lake system. This graph here is measuring the amount of organic carbon that has accumulated in the sediments through time. And that is a crude measure of how productive the lake has been through time. And what it's telling us is that over the last 10,000 years, since the ice left the drainage basin, biological productivity has been slowly increasing, increasing, and increasing. because that line is shifting more and more to the right. We get another measure of that productivity from this parameter, which is the carbon isotopes. I won't go into that. But what I do want to point out is that, yes, we've had gradual change over 10,000 years of change in this lake, but look at that, right up at the top. We're seeing a dramatic change that has been going on since just 1950. It's off scale. It's much faster than anything we've seen in the last 10,000 years, and it means the fundamental biological system in this lake is changing in ways that we don't yet understand. Is it due to global warming, or is it due to the perhaps invasive species coming into the lake? We don't have the answer to that yet. But the fact that most of this change has happened since 1950, whereas the lamprey came in well before that, it suggests to us that maybe we're looking more at a temperature effect than we are at an exotic species effect. So these are very important changes that are happening in this gorgeous, important, big lake in our backyard. And we're doing our best to figure out just what is going to be the response as the lake continues to warm. And undoubtedly, it will continue to warm as CO2 increases in the atmosphere. So I conclude with Lake Superior is warming at a surprisingly fast rate. The lake's biology is also changing rapidly, much faster in the past 5 decades than at any time in the previous 9,000 years. We do not yet know the lake ecosystem well enough to predict the consequences of these changes. And finally, I've just been talking about Lake Superior, but we have hard data from Lake Malawi, where we work regularly, from Lake Tanganyika, where colleagues of ours are working, from Lake Baikal, where other colleagues of ours are working. We're seeing the same trends in these tropical lakes. There is big change happening in the Great Lakes of the world. They're terribly important. We need to get our heads wrapped around it. Thank you.
Okay, and can you hear me? People hear me? I'd like to thank Brian and on behalf of all three of us for inviting us to talk to us. I'm going to wrap this up by bringing it home like Tom did on the lake, but on the land, talking about the effects of climate change on Minnesota's forests. And we all live up here because we want to live next to the beautiful Great Lake with clean water, and we want to live in these kinds of forests. There's nothing wrong with Nebraska, but I would say that if any of us want to live in Nebraska, we would move to Nebraska. And unfortunately, it looks like Nebraska might move here. So, here we go. There is a very tight connection between the distribution of forests and prairie in Minnesota and the climate. And this map shows exactly why we don't need much of a change in climate to change the vegetation when you're at the boundaries of these things. This map here shows the pre-settlement forests of Minnesota before European settlement from the surveyor's records when they were laying out the township and range survey. Every quarter section, they measured the distance, diameter, and species of a tree in the landscape, and we can take those records and reconstruct with quite accuracy and detail the pre-settlement forest. And you can see, just in this map, it's divided up into forest in green and prairie in yellow, and right here is the prairie forest border. It's actually quite sharp if you drive west of here at any time. You know, once you get west of Grand Rapids, west of the all of a sudden, trees are gone and you're in prairie. What that's related to is the water balance. This shows the difference between precipitation, rainfall, snowfall, incoming water, and PET is potential evapotranspiration. What that is the water being lost by evaporation from water surfaces and also through leaves. Leaves lose water as they transpire water. They take water up and water goes through and it goes out through pores in the leaves. The bigger this difference is, the more water you have. So this difference is actually kind of a measure of drought stress. So you see up here in the northeastern part of the state, this is in millimeters, 494 millimeters of the difference between those two. We got plenty of water up here, as you can see if you drive around the landscape. You get out in the prairie, and all of a sudden now you're down to zero, where precipitation is exactly balanced by evapotranspiration, so you're on the edge of a drought stress. And then you go into the Dakotas, and you're well below zero. That's why the Dakotas don't have trees. No water, no trees. Okay? It's just very low precipitation, and a lot temperature affects this evaporative demand. So as temperature goes up, this goes up, and you end up with a drought stress problem. So you see there's a very tight coupling. All you have to do is move this red stuff east, and you can see there'll be great changes in vegetation. And in sediment cores, like Tom showed for the lakes, we also look at the pollen record. And in the past, actually, when it's gotten warmer, during that period about 6,000 years ago, during what's called the hypsothermal, this prairie border came all the way over here, almost into Duluth. So we know what's happening in the west already. Okay, back in the 1980s, a bunch of us, I was at Oak Ridge National Laboratory then, we were developing forest models based on data that largely was collected by the Forest Service. The growth of trees, the production of seeds of trees, how trees respond to temperature, water, stress in soil, and so forth and so on. And we were making these forest models to look at growth of forests and what predictions can we make for timber harvesting and everything else. And one of the things we started doing was looking at effects of climate change on the growth of trees. So these models work by taking a plot of land and simulate the growth and depth of a bunch of trees on there, and they grow through, and sometimes the big trees die, or you cut them, and little trees come in, and so forth. And my part of it, along with Mac Post, was to simulate what happens in soil, both the water balance in the soil, and what happens when the leaves fall and they decay and compost the soil and release nutrients, and we have nutrient uptake and so forth. And so what we did was we took these models and we started growing the forest, and then we started driving them with the predicted changes in climate to see what happened. So I want to show, and I wasn't in Minnesota then, and I had no idea I would end up here. And we did this for about 50 sites all over eastern North America, on both the clay soil that can hold a lot of water and the sand that can't. And lo and behold, Minnesota turned out to be the biggest change in all of eastern North America, largely because we're right on the edge of that balance here of what is happening with precipitation and the boundary between forest and prairie. So let me show you what we found. And this was published back in 1988, which was the same year that the first model was published that Professor Gallup showed you, that showed unequivocally that you cannot account for the observed changes in temperature without putting the CO2 warming effect in the model. So these papers were published in exactly the same year, in the same journal, actually, Nature. And so here is on a clay, and like we have around in Duluth. Here's on a sandy soil or a rocky soil, like you'd have in the boundary waters of west of here out towards Grand Rapids. And we started with a bare ground, and we let it generate whatever kind of forest was appropriate for that area. We ran it for current climate for 200 years. And then we started a warming and drying trend for 100 years, and then ran it for 200 more years. In this case, the prediction for Cloquet, Minnesota was about a 4-degree Fahrenheit warming, roughly about a 2-degree centigrade warming, a little less, and a drop in precipitation and drying right around here, about 20%, which does correspond with kind of what happened during that warm period 6,000 years ago. And what happens during that 100-year warming is at first, nothing happens for the first 30 to 40 years until you exceed the temperature tolerance of spruce. Spruce goes out, well, let me back up. Before that, under current climate, you see aspen coming in, and eventually the aspen dying out like it does because it doesn't live very long. And succeeding to a mixture of spruce and maple and birch. This was largely yellow birch, a little bit of pine on clays, but pretty much the kind of forest that we have around here. And this is the above ground biomass, so the total weight of the forest over here. Once we start warming, nothing happens until we exceed the temperature tolerance of spruce. Spruce dies out, maple expands, Maple, the leaf litter actually is rich in nutrients, it composts the soil, it makes the soil richer, and productivity goes up. And other things start to invade the forest, like basswoods that we don't have a lot of here. So what we get is a switch from north woods type forest to a northern hardwood. Basically what's happening is we do have some maples here in northern Minnesota, but more than maples are moving out from Wisconsin around the lake and moving northward. If we look at what happens, exact same climate forcing on a sandy or rocky soil that can't hold much water. So here we have less biomass, it's less productive, a lot less maple. Maple is not very drought tolerant at all. More pine, a little more birch. With the warming, everything collapses. And you end up with this sort of scruffy oak, jack pine, prairie, savanna kind of thing. No water, no trees. Okay? Now, if we warm this any more than this, or if we dry it down any more than that, this is actually kind of what Professor Gallup was showing as the low emission scenario. If we warm it any more, the high emission scenario, everything looks like this, even on the place. The place simply cannot hold enough water to counter the evaporative demand. Lou Iverson with the Forest Service later on took a very different approach, much more detailed. This is the current distribution of forests in the Great Lakes, the upper Midwest, the Lake States region. And I want you to look in particular at what happens with this, the blue, the white and red pine, and this kind of blue here, the spruce fir, which we have in northern Minnesota, and then this kind of lavender, the aspen birch berry. So you can see right here, this is the northwoods, the aspen birch, spruce fir, and maple, this chartreuse kind of color, whatever it is, in northern Wisconsin, northern Michigan over here. Under the lower emission scenario from the IPCC, and this was a previous lower emission scenario, but roughly corresponding with what Professor Gallup showed us, the most recent lower carbon emission scenario. The spruce fir is lost, except for maybe a little bit right around Grand Marais. The aspen and birch are still around here a little bit, but it moved real far east. And this lighter blue here is an Elm-ash cottonwood. That's the kind of stuff you see out in the prairie, okay, with prairie mixed in with it. Under the hot, and you see the maples starting to move around a little bit here, maybe even expanding. Under the higher emission scenario, the spruce fir is gone, the aspen birch is gone, the Elm-ash cottonwood, this is associated with the prairie, has moved all the way east to Duluth here. The maple is maybe right along Lake Superior, maybe. And oak hickory is in northern Minnesota. So the northwoods is gone, whether you look at our scenarios or Lou Iverson scenarios. Okay, those are predictions. What's been happening? There's a paper from Global Change Biology in 2011, a couple of years ago, right on the edge of the boreal forest in Canada prairie border, right over here. A massive mortality of aspen following severe drought. This is all aspen. This is in the middle of summer. This is not fall that the aspen has lost its leaves. This is in the middle of summer. Basically, the prairie is already starting to move into the border forest a little bit northwest of here. Lee Freilich from the University of Minnesota Forestry Department down in the cities. Lee and I were grad students in the forestry school in Wisconsin together. Lee's been following changes in vegetation in the boundary waters in Seagull Lake, in Saginaw Lake, and other places. And this shows his data on for what is happening to the growth of trees, the height growth of trees. The blue is balsam fir and white spruce, the spruce fir forest, the northwoods. And the red are things like red maple, sugar maple, and red oak right here. And you can see the height growth over the study period was 2005 to 2009. The height growth has decreased for spruce and fir, and it's increased for the maples and the oak, exactly as we predicted, but only under low browsing pressure where there aren't deer. The surprising thing is, in places where you have a lot of deer, the spruce and fir are still declining because deer don't browse those, but the deer are keeping the maples and the oaks from growing. So the New Jersey climate is complicated. The response of the forest to climate depends on deer and how much the deer population is holding back the regeneration and growth of the things that will replace the spruce and fir. And we didn't have the effects of deer browsing in our model, and Lou Iverson didn't have it in his model. So there are some complications. So the other thing that Lee points out, and I think this is a very good point, here's our forest today. This is the boundary waters that we all know and love, that we've all canoed in, my son canoes in. Everybody loves that. This is the forest of today. The forests of the future are going to look like this kind of scrappy oak, pine, open savanna. You know, in a lot of ways, that's not a bad-looking forest. Great grouse habitat. You can hunt grouse in there. You can hunt deer in there. It's actually not a bad kind of forest. I don't want to live there. I'd rather live here. But here's the thing. In the intermediate stage, we're not going to go from this to this overnight. The intermediate stage is going to be a very, very messy transition. This forest has to die back before it's replaced by this. And this is what we're going to see. Massive wildfires coming in on the droughts, killing a lot of things, grasses coming in before the oaks and the maple can regenerate themselves over here. How fast is this going to happen? You know, I stopped talking about this in terms of years, because if I told you, well, maybe 100 years to get from here to here, say rightly, you know something, I got to go pick up milk at the store, I got to pick up my kids at soccer practice, I'll worry about this all the time. Let me put it a different way in terms of generations. I'm 61 this year. My generation and the Congressman's generation is the last generation that will live out their lives in this kind of forest. My son, at the end of his life, this will not be here if we keep going the way we're going. My grandson, who was just born 3 weeks ago, will spend most of his life in this. He will not even remember this if we keep doing what we're doing. So in terms of generations, it hits home real quick. So, what should we do? Well, from a forester's standpoint, what we have to do is do whatever we can to slow this down and stop it. But in the meantime, plant or favor drought-resistant species like red oak or jack pine, especially on sand or drought or rocky soil. Favor maples on heavy soils that can hold a lot of water or where moisture is favorable at the bottom of the valleys. Heavily control the deer herd. We have too many deer. That is impeding our ability to generate the forest. And the Nature Conservancy, I noticed Mark White is here. Is Meredith here? Meredith Cornett? Meredith here? Mark and Meredith are from the Duluth chapter of the Minnesota Nature Conservancy. And I'm proud to say that I'm now on the board of the Minnesota Nature Conservancy. But they've been doing excellent work for the last couple of years, working with local landowners to implement these kinds of strategies up here to get a forest into a more resilient shape where it's ready to respond to whatever kind of climate change happens, or stays the same if we can slow it up from happening. And I urge you to talk with them about exactly what they're doing, because I think it's great work here in northern Minnesota. And finally, get political. A colleague and I were talking a while ago, and this was before the congressman was elected. So what I'm going to tell you, what we said doesn't apply to him, because he wasn't a congressman. But we're both old enough to remember Gaylord Nelson, Willard Munger, Bruce Bento. All the gray hairs in the audience are nodding like this, like mine. You youngsters need to know who these people are. Gaylord Nelson was a senator from Wisconsin. He was the founder of Earth Day. Bruce Bento was a biologist before he became biology teacher, before he became a congressman from the Twin Cities area. And I had the great fortune of working with Congressman Bento on a number of environmental issues. And what he always wanted to know whenever we met was, don't talk to me about politics, just tell me what kind of biological research you're doing now. I just want to hear about biology. He was great. And Willard Munger, the Dean of Environmental Legislators here in Minnesota, represented West Duluth. These were giants in the earth in those days. These were three gentlemen who were passionate defenders of the environment and knowledgeable. They wanted to know about the science. They wanted to know about what was going on so they could better represent what was going on in Congress and in the state and write better bills. And this colleague of mine and I, we were talking and we were saying, so where is the Bruce Bento of today? Where is the Gaylord Nelson today at any level of government? And we couldn't think of it. So, and again, this was before the congressman was elected.
Thank you, John.
Anyhow, my point is, we desperately need informed, passionate defense of the environment, and particularly about this issue of climate change at all levels of government. From the city council, the county commissioners, all the way on up to the presidency, at every level of government. And it's up to us in a democracy to see to it that that happens. But we do not have that now at any level of government. I think we have people who potentially could do that, but we need to encourage them and vote for them. And when they come around and ask for your vote, to say, what do you think about this issue? What do you hope to do about this issue? Because the North Woods is going to be gone. It will be gone if we don't do it. So that's the end of my spiel.